We're going to continue talking about graphs in this lecture, specifically about different kinds of symmetry. So a graph can have three kinds of symmetry. Symmetry about the y-axis, where if you took the graph and folded it along the y-axis, the two pieces of the graph would match, lie on top of each other. So the y-axis is like a mirror. Then we have symmetry about the x-axis, same thing. If you were to fold your graph paper along the x-axis, the two halves would match. So the x-axis is like a mirror. Oh, well, we haven't discussed the definition of a function yet, but yeah, this is not a function. Yeah. Yeah. The day we talk about functions, remind me of that. And then the last kind of symmetry is called origin symmetry. And that's one where if you fold along the x-axis and the y-axis, so you'd be like folding this paper into quarters. So when I fold over the x-axis, this upper piece is going to come down here, like that. And then when I fold over y, it'll lay right on top of the other piece. And that one's called origin symmetry. Fold over x and y. So we can just look at a graph and say whether or not we think it has symmetry. We also have algebraic tests for symmetry. So you can test if a graph is symmetric about the y-axis if you can replace an x with a negative x and still have the same y value. Okay, so here's a picture. These 2 points are symmetric about the y-axis. The y-axis is like a mirror because one goes right x and the other one goes left x, and they both go up y. So if I replace the positive x with the negative x, I would get the same y value. Now, to test for x-axis symmetry, you replace y with a negative y, right? These 2 points are symmetric about the x-axis. And if you replace the y with a negative y, you should get the same x. This one's positive y, this one's negative y, but they're both the same x value because they both went over x, and then one went up y and one went down y. Okay? And then the final test is the test for origin symmetry, where you replace x with negative x and y with negative y. Okay, so these 2 points, this one and this one, have origin symmetry. Picture the folding. If I were to fold it in half along the x-axis, this one, this red one right here, would move down to here. And then when I fold over y, it would land on top of this one. And this point goes right x, up y. And to get to this point, you go left x, down y. So if you replace x with negative x and y with negative x, you'll have the same equation. So this picture can kind of remind you of what all the tests are. So let's do one. Let's do an algebraic test for symmetry in the equation y equals the absolute value of x. So we can look at a picture of it and say, yeah, that definitely looks like it has y-axis symmetry, right? To test it algebraically, you start with the original equation, and you replace an x with a negative x. You replace all the x's with negative x's. So this says y equals the absolute value of negative x. But what is the absolute value of negative x? Right, it's the same as the absolute value of x, right? The absolute value of a number and the absolute value of a negative number are the same. So my equation remained unchanged. That's how I know that I have y-axis symmetry. If you can replace the x with a negative x and the equation is unchanged, then I have y-axis symmetry. Okay so far? Okay, so now let's do a test for x-axis symmetry. Here's the graph of y squared equals x. I drew a picture of it, or my computer drew a picture of it, and it definitely looks like it has x-axis symmetry. To double check, I can do an algebraic test. Start by writing down the equation, and the algebraic test says replace y with negative y. So instead of a y here, I'm going to put a negative y. But what is negative y squared? It's just y squared, right? Because when you square a negative, it becomes positive, because negative y times negative y is going to be positive y squared. What do you mean?
You're using the square to get it to a positive y. So the square would still be there though?
Yes, it's still squared. Yeah. Right. Okay, I understand the question. Okay, so y squared equals x remains unchanged. Even after I made all the y's negative y's, the equation is still the same. So I have x-axis symmetry. Okay, so let's look at the last kind of symmetry. Origin symmetry. So here is a picture of y equals x cubed. I graphed y equals x cubed. It definitely looks like it has origin symmetry. If I did the double fold along the x-axis and the y-axis, it looks like the two pieces would match. To double check, I can do an algebraic test. Start by writing down the original equation. I'm going to replace the x's with negative x's and the y's with negative y's. So this is going to be negative x cubed, and this is going to be y cubed. Oh, sorry, negative y cubed. Make the x's negative and the y's negative. Oh, it's not cubed. Thank you. Oh, okay. Okay, so I replaced the x with a negative x, replaced the y with a negative y. There we go. Okay. Okay, negative x cubed, that's negative x times negative x times negative x. Is the answer going to be positive or negative? Negative. So this is negative x cubed equals negative y. Hmm? Right. Why didn't it change? Yep. Very good. So this equation, negative y equals negative x cubed, is equivalent to y equals x cubed, because you can either think of it as multiplying or dividing both sides by -1. That would give you y equals x cubed. Or you can just think of them as trading places. I'm going to add y to both sides and add x cubed to both sides. So they just swap spots. Okay, but either way, you get y equals x cubed. So even after I made the x's negative and the y's negative, I got back to the original equation. It's unchanged. Therefore, I have origin symmetry. Sorry, I should have mentioned, I don't know if you know this, these three dots in a triangle means therefore. It's a mathematician's symbol for therefore. Sure. Okay, so here are 3 equations, and I want to test them for the 3 different kinds of symmetry: y-axis, x-axis, and origin. So I'll do the first one with you. Do this one. We want to test it for, I have no idea what it looks like. I don't have a graph. I can't graph that in my graphing calculator because it doesn't look like y equals some stuff. So the only way to tell what kind of symmetry it has is to do an algebraic test. So I'll start with the y-axis test. The y-axis test replaces x with negative x's. Okay. So in here, I replace every x with a negative x. And is that equation equivalent to the original? No, and it doesn't look like the original. There's no way to make it look like the original. I could try multiplying both sides by -1 to make the x, back the way it was, but then I end up with negative y to the 4th plus y squared, which is not the original either. So I can't make this into the original no matter how much playing around I do. So I have no y-axis symmetry for this equation. So let's try x-axis symmetry. So the equation is x equals y to the 4th minus y squared. This is the original. So the test for symmetry about the x-axis is to replace y with negative y. So for both of my y's, I'm going to replace them with negatives. So I get x equals negative y to the 4th minus negative y squared. So just in each place I saw a y, instead I wrote a negative y. Now what is negative y to the 4th? Positive y to the 4th, because it's negative y times negative y times negative y times negative y. 4 negatives make a positive. So I get x equals y to the 4th. And negative y squared is the same as y squared. That is equivalent to my original. So yes, I have x-axis symmetry. All right, let's do the last one. I want to test symmetry about the origin. So to test symmetry about the origin, I replace x with negative x and y with negative y. So I'm going to have negative x equals negative y to the 4th minus negative y squared. There's nothing I can do to simplify negative x any further. Negative x is just negative x. But negative y to the 4th is y to the 4th. And negative y squared is y squared. Is there any way to make that look like the original equation? No, it's not equivalent to the original equation, so I have no origin symmetry. So an important question might be, once I found that it had x-axis symmetry, could I just stop? Could I just say, oh, I found the kind of symmetry it has, I'm done? That's the question. Can something have more than one kind of symmetry? We can definitely have all 3. Yeah, let's see. What kind of graph would have all 3 symmetries? A circle. Circle centered at the origin. has X, Y, and origin symmetry. Is there anything that would have 2 of the 3? You would. Yeah. So no, you either have 1, none, or 3. Yeah. All right, so I'm going to let you in your groups try the next 2. Test the next 2 equations for all 3 kinds of symmetry. Okay, last thing about symmetry is that you should be able to complete a graph if you know something about its symmetry. So for the example on the left, I have part of the graph drawn and I told you it's symmetric about the y-axis. So you can just treat the y-axis like a mirror to try to draw the rest of the graph. And if that's difficult for you because you know, you have to have a certain kind of ability to visualize to do that, then one way to do it is to pick some important points and label them. So I'm just going to pick some of the important points here, sort of the corners. And this would be 2, 1. This one is 2, -1, 3, -1, and 5, 1. So remember, y-axis symmetry, the test was you can replace x with -x. That's how you reflect something over the y-axis. Instead of 2, 1, make it -2, 1. And instead of 2, -1, make it -2, -1. Just take the opposite of all the x values. So instead of 3, -1, we're going to do -3, -1. And instead of 5, 1, we'll do -5, 1. And then just connect the dots. No, I think it just, sometimes it's like slow. Oh, yes, it can, yeah. Yeah. So for origin symmetry, I find that the most difficult one to visualize. So I always do this one by points. Again, choose the important points. This is 0, 3, 2, 1, 2, -1, 3, -1, and 5, 1. And then the test for origin symmetry was replace x with -x and y with -y. So I'm going to take the opposite of both coordinates. So instead of 0, 3, well, what's the opposite of 0? It's still 0. So instead of 0, 3, it's going to be 0, -3. And instead of 2, 1, it's going to be -2, -1. Instead of 2, -1, what's my new point going to be? -2, +1. Yeah, take the opposite. And instead of 3, -1, I would do -3, +1. And instead of 5, 1, I'll do -5, -1. So this is my reflection over the origin. Yeah. Okay, so the first thing we need to do is turn it on, right? So to turn on your graphing calculator, the on button is in the lower left over here. Turn it on. Okay. So you can turn it off by pressing second off. It also has an it also automatically turns off if it's inactive for a certain amount of time. Hit the mode button by accident. and you're like, shoot, what is this menu? How do I get out of here? Whenever you're lost and you don't know where you are, you just hit quit. So quit is right here, and it's written in yellow. So in order to use the quit button, you have to press the yellow button first. So you do yellow, then quit. And it brings you back to, this is called the home screen. Okay. All right, so in the home screen, you can do all kinds of things, right? You can do 2 plus 3, and there's no equals button. You use the enter button instead of equals. Gives you 5. So now let's do 25 plus 3. And instead, don't hit enter though. And instead of using, let's say we said, oh shoot, I wrote 25 plus 3 and I meant to write 2 plus 3. You can use the arrows and the delete button to get rid of the 5. Okay. And let's say you deleted it and then you said, oh no, I wish I had it there. I really meant 25. You can use the insert button, which is right above delete, to put it back in. So you hit yellow and then insert, and you can type the 5 back in. Okay. Okay, so we're going to skip down to G here. To find 7 squared, you can either hit 7 and then the x squared button, enter, or you can hit 7 caret 2. So the caret is the exponent. This little guy, the caret or the hat, whatever you want to call it, also means 7 squared. So you can find 2 cubed that way, right? You hit 2 caret cubed, enter. There's no special cubed button. All right, and then let's hit clear a few times so that we have a nice clean home screen. To find square root 9, square root is right here, right above squared, like halfway down on the left. So it's in yellow, so you have to press the yellow button first. And you get 3. And then for cube root 8, you can do it 2 ways. They're both in the math menu. So if you want to do cube root or 4th root or 5th root, you always go to the math menu. You can either choose option 4, which is cube root, type in 8, or you can press the 3 first, go to the math menu, and choose the xth root. Okay, you can do that too. Yep. Yeah, that's a good point. You can also do 8 to the 1/3 because cube root and the 1/3 power are the same. So you can do that also. Okay, if we want to do absolute values, that's also in the math menu. So once you're in the math menu, you can see there's 4 sub-menus across the top. If you go over to number, the first option is absolute value. Choose that and type in absolute value of -4. So it doesn't give you the bars, like which are our normal symbols. It just says ABS, open parentheses. So it's just saying, what do you want to take the absolute value of? Type it in and hit enter. And it gives you the absolute value back. All right, so let's see, for adding fractions, let's see, what happens if we do 1 divided by 2 plus 1 divided by 3? That gives us a decimal, right? If I want the fraction, what should the answer be, by the way? What's 1/2 plus 1/3? 5/6. So we want to know if this is 5/6. You press the math button. The first option says 2 fraction, arrow fraction. So choose that, and you get 5/6. So good. All right, let's type 4 plus 5, enter. And you go, oh, I wanted to take the square root of that. So instead of typing the number 9 over again, especially if that number were like 6 digits long, if you didn't want to retype them all, you can just take the previous answer by doing yellow and then the negative button down in the bottom. In yellow above it, it says ANS for answer. And it gives you the square root of the previous answer. All right, so let's just move down to P here. With division, you do have to be careful with parentheses. So if I want to do 10 over 2 plus 3, do it in your head. What should the answer be? 2. It's 10 over 5, which is 2. But if I type in 10 over 2 plus 3, your calculator knows the order of operations, and it's going to do 10 divided by 2 first and get 5, and then add the 3 to get 8. So you need parentheses around the 2 plus 3. So if I want to pull this up again, I can hit second, enter, and it just gives me exactly what I just typed in, and you can edit it now with the arrows. We'll add some parentheses. And now we get the 2 that we were looking for. Second entry. So you do second and then the enter button. That little trick is really handy when you're trying to do like plus or minus in the quadratic formula, because you can do the plus and then you hit second enter and it gives it again, and all you have to do is change the plus to a minus. Saves you a little bit of typing. Okay, we're going to skip this. Okay. To set something as x, like, okay, so let's say you want 52 to be x. You type in 52, and then you use this store button right here, STO, and you can store it as anything you want, any of the letters. You could store it as A, oops. So to store it as A, you have to press the alpha button, because A is written in green or blue or whatever yours is. Right? Or you could store it as X. You could just press the X button, or you can type alpha X. It's the same thing. So then if I wanted to do 2 times X, it's going to use X value of 52. How do you clear it? You don't clear it, you just replace it. If you want X to be something else, you type, like, let's say now we want X to be 13. Store that as X, and it just overwrites it. Okay. Oh, it looks like a theta. That's a Greek letter. Yeah, it's a Greek letter that we often use to name an angle. Yeah. No, although it does look the same, right? Yeah, it looks like an empty set, but this is just a Greek letter, theta. All right, so we clear that all out. To graph stuff, you can press the y equals button, and you have all these things you can type in. So we're going to graph this equation, x cubed minus 3x squared plus 2. So you use this x button here. It says xt theta n. It generally is going to mean x for us. So you hit it, it types x cubed minus 3x squared plus 2. All right, so this is going to be much more complicated than a line. So, why are you doing this? Okay, so now press the zoom button. So what we have to do is we have to decide where in the coordinate plane we want to look for this graph, because the coordinate plane is an infinite thing. right? The x-axis goes left and right infinitely, and up y-axis goes up and down infinitely. And we just have this little tiny box on our graphing calculator. We have to decide where in the coordinate plane do we want to look. So the standard window is option 6, and that's just -10 to 10 for x and -10 to 10 for y. And that's a graph of the equation. Yes, you can. Yep. Oh, okay. You have another line. Go back into y equals. Do you have something typed in another one? Yeah. So yeah, you can graph more than one equation at once. So I could also graph, say, 3x plus 2. And then I could graph both of them and see both graphs at the same time. So that can happen a lot. You can forget that you had something in there, and then you graph and. Okay. So there's my graph. Now let's say I'm really just interested in this bit right here. Okay. I'm just interested in this part. I want to be able to see all 3 x-intercepts and this maximum point and this minimum point. So I have a couple of different ways I could get a better window. I could put it in manually by pressing the window button. And let's see, for x, maybe I'll go -2 to the left. And how far to the right do you think I should go? 4? -2 to 4 for x. So go to window, type -2 for x min, and 4 for x max. Now, I generally always keep the x scale at 1. That just means how big is a unit between tick marks. And then for y, we'll graph this, and then we'll change y as needed. So we changed the x values there. Now, for y, I don't need to go down this far, right? Maybe -3 would be far enough, and 3 as a maximum, too. So go back to window, type -3 to 3, y min and y max. Everything else in here in this menu, I just always leave the same. You change x min, x max, y min, y max, and everything else I always just leave the same. And then hit graph. And now we get a zoomed in picture of our graph. Yep. Zoom 6 gives you a standard window, which is -10 to 10, -10 to 10. Let's do that. Well, let's not. Save that for another day. Okay. So if you want to graph something that looks like, in order to graph something in your calculator, it has to be in the form y equals something with x's in it. So let's say I wanted to graph the equation x times y equals 5. What would I enter into my calculator? Y equals 5 over x, exactly. So I'll clear this, and I would do 5 over x. And then I could hit zoom 6, because that will just give me sort of a good starting place often. And I get this graph. So deciding what window to use is an art. It takes a lot of practice. We'll do more of it next class. And we rushed through that, but hopefully it's enough. And we'll do more. We're going to do more with calculators next class.